the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Thank you for joining us today for our new AI for Good energy webinar. For those interested in our earlier webinars on fusion energy, I will put a link in the chat or in the comments, depending on if you are watching us live or on YouTube. My name is Priscilla Oforiwa, and I work at the International Atomic Energy Agency. Our work at the IAEA is to foster collaboration and coordination on fusion R&D and move forward in developing the peaceful uses of fusion energy. We've been doing this work since 1958. Let me warmly welcome our speaker for today, Professor Egemen Coleman, who has kindly devoted his time to present with us today on AI for plasma control in fusion energy. Professor Coleman will discuss the importance of maintaining a high-pressure hydrogenic plasma without disruption for efficient fusion energy production using a tokamak machine, and will explain the necessity of active control of the tokamak based on observed plasma state to manage high-pressure plasma while avoiding tearing instability, which is a major cause of disruption. Professor Coleman is an associate professor at Princeton University's Mechanical and Aerospace Engineering, jointly appointed with the Adelinger Center for Energy and the Environment and the Princeton Plasma Physics Laboratory. He is the director of the program in Sustainable Energy, recipient of David J. Rose Excellence in Fusion Engineering Award, and an ITER Scientist Fellow. He currently leads research on machine learning, real-time diagnostics, and control at K-STAR, NSTU, and DIII-D. Please type your questions and comments in the chat box, and we will try to go through your questions during the Q&A section at the end. For those of you working or interested in fusion or plasma science, make sure to check our IAEA Fusion portal. I will share the link in the chat. Without further ado, I give the floor to Professor Egemen Coleman. Thank you.
Hey, hi everyone. Just want to get confirmation that my screen is being shared properly.
Yes, it is, yeah.
Okay. 1 second. Okay. So, hi everyone. It's great to be here for the AI for Good presentation here. I'll be talking about fusion energy in general, a bit broader than what Priscilla said. I just want to see what we use for AI in fusion energy. And it's great to be part of AI for good. It's much better than being part of AI for evil, even though I would have liked to have a mini me next to me. So this work, obviously, I'm a professor. It's done mostly by the postdocs and the grad students in my group that are shown here. These are the youngest members. These are my kids. And we did this work in multiple fusion reactors in the world that are listed below. Fusion is the main source of energy in the universe. And if you look at the energy on the world, when you look at wind energy or solar energy or hydro energy, these are all converted forms of fusion energy. Fusion energy becomes light and it comes to Earth, and it drives the wind cycle, or it can convert into plants that die off and become fossil fuels in millions of years. But what we want to do is to make use of fusion energy directly, convert fusion energy into electricity directly. And that's what we are working in the magnetic fusion. The idea is pretty simple. We take small molecules, atoms. We take hydrogen atoms, deuterium and tritium. These are isotopes of hydrogen. If you can give enough velocity and energy to these, they hit each other and fuse. And when they fuse, they make helium and produce a lot of energy. And we harness this energy in terms of electricity. So to keep, to get the particles to hit each other, you need to confine them because they're energetic, they have high velocities, they want to escape. The best way to confine particles that are ionized is to use a magnetic field. If you put a South Pole and a North Pole, and you make a magnetic field, neutrals, electrons, and ions gyrate around this magnetic field. This is great, so they're confined, but at the end, they hit the wall at the ends, the magnets, and the confinement ends there. So what you can do is what's called the tokamak concept. You take this and you turn it into a donut. So you turn the plasma into a donut, and you confine it in this magnetic cage. So that's the type of fusion reactor that I'll be talking about. There are other ways as well, but this is the most advanced version, which we think we can make electricity in the near term. So what is the progress? We have been making a lot of power. This is fusion power versus years. And we went from in the 1950s, 60s, this started, and we make a lot of progress to producing tens of megawatts of power. But these are not net energy producing machines. The next step is ITER, which is in France. It's a collaboration between multiple countries that's going to produce about 500 megawatts of energy. That's 10 times the input energy that we put. So it's going to produce 10 times the energy we put. And the aim is to finish this soon and operated in the late 2020s. And this is the size of this reactor. This is a person here, and this is me by ITER as well. I work at ITER as well, and you can see the scale of this machine. It's quite big. But that's not the only thing. It used to be only the countries and federal agencies were developing this, but now there's a lot of private companies. You see the number of companies that are shooting up. There's almost 50 right now, and billions of dollars have been invested. There's some of the companies, and they're trying to make fusion a reality as well. And I work with a lot of these companies. So one of the big issues with tokamaks is the instabilities that might lead to a disruption. So all the energy that you confine in your fusion reactor basically hits the wall and dissipates all the energy. So here's an example of this from CMOD. So this is initiation of the plasma, and plasma is formed. Now you see, and all of a sudden the plasma ends. I'll go back here to show you. So this is the plasma, and all of a sudden you see the fireworks. This fireworks is basically when the plasma hits the wall, it's making tiny bits of metal, and they're sparkling around. So this happened, as you see here, extremely fast. So it's not easy to control this. So what you want to do is to avoid it. So when we have a stable plasma, this is the plasma, and this is the tokamak reactor. It becomes unstable in multiple seconds time scales. It's an unstable plasma. But once it becomes unstable, like I showed in the video, it grows really fast and hits the wall in millisecond timescales. So it's very hard to stop this process. And once you get there, then you might hit the wall. Here's an example, and damage the reactor. So we want to, and this is a problem for ITER and future reactors. So if you want to stop this process, you want to make the plasma, avoid the plasma becoming unstable. So you want to keep this away, because once it's unstable, you can't stop this process. So once it's unstable, it's not unstable, then you can stop this whole process going forward. But as I said, this is happening really fast. You can't have a driver kind of steering the plasma. What you need is a computer system, a real-time disruption avoidance, or some computer system that can do analysis of what's happening in the plasma and take action if something happens. So to do that, we need control, and machine learning helps us in AI, and machine learning helps us in designing this control. So when we talk about control, we think of a desired output. So for example, we say we don't want any disruptions, but we do want a lot of power. This is what we want. We have some sort of a controller. That's our hammer. The plant here is the reactor, fusion reactor. Then we feed this back with our measurements. So that's the eyes. So you put this together and you have a full control system. So first I'll talk about the measurement devices, because to be able to take action, you need to see what's going on. And in a reactor, we have many diagnostics. And here's an example for DIII-D. You see dozens of different types of diagnostics, which is not going to be the same in a reactor, because reactor has neutronics and it's going to be damaging some of these things, so we can't have as many as we do right now. So the question becomes, as we go from current reactors to ITER to a demonstration power plant, we are in a nuclear environment, and we are going to have minimal diagnostics. And because it's a nuclear environment, we're going to have faults, failures due to these neutrons. How can we make robust diagnostics, and how can we make how can we choose the minimal diagnostic set? So here, machine learning AI can come to the rescue. And to understand how it can help us, so I'll first talk about the plasma state. Plasma in the donut that I was talking about, this is the plasma. We can define it as the shape of this. So this is the shape, the nested sort of surfaces, the flux surfaces, we call them. And the second part of it is the profiles. The profiles start here at the core, 0, and goes all the way to 1. Because the transport along these lines is so much, we can only we need to only consider the profile along this line. So we have the temperature and density and so forth. There's about 6 of these profiles. So our state is the shape and these 6 profiles. And our aim is to find these so that we can do good control. So first we have to find the shape. This is used by a nonlinear PDE. It's called the Grasser-Funnell equation. The equations are here, which is not that interesting, but we use these diagnostics, Thomson scattering, charge exchange, etc., to find the PDE that matches the measurements the best. So that's the fitting process. It's called the RT fit. So historically, this was done by running a code, physics-based code. So we take the diagnostics and we convert it into state by fitting. And we made some surrogate models, which I'll talk about, and that runs in real time. So convert this into machine learning-based immersion. So what are we trying to do here? We take the diagnostics, and we want to find the equilibrium, the shape, using the inversion of this partial differential equation. And we have to do this really fast. So we make a neural net version of this. And what you can see here is the offline analysis, EFIT-01, versus the EQNet. This is the neural net version. You can see that they're pretty much on top of each other. So the surrogate model gets you the results as good as you would do offline. But the nice thing is that if you look at the real-time version of this code, it cannot do all the physics analysis because there's not enough time. So what happens is that, for example, here you see the offline version versus EQNet. They're on top of each other. And then there is a delay of about a few milliseconds, 5 milliseconds on the real-time calculations. So, and there's other issues related to dynamics. When things are changing too fast, the real-time calculations cannot catch up if you're doing the physics space. But neural nets can get exactly the same thing. So what this leads to with the real-time construction, which is not that good, is you get these bean-shaped plasmas sometimes, which lead to plasma disrupting afterwards. And these time delays leads to control that's not being that good. So our neural nets reconstruction allows us to make much more stable plasma. In this case, stability allows us to stretch this plasma and make it as elongated as possible. And this allowed us to get the highest elongation discharge on NSDX upgrade. This is simulation of that. So, okay, so we got the shape. Now we want to find these profiles. These are, like I said, the density of the ions, density of the electrons, temperature of the electrons, etc. And for that, we developed this code called CAKE. It's consistent automatic kinetic equilibrium reconstruction. And basically finds all these different parameters by doing a consistent analysis of the diagnostics. It takes a long time. It takes about minutes to do. So we made a neural net version of it as well. It's a surrogate model. So this takes all this, and it takes all the inputs of the diagnostics and the compute that we do offline and make a neural net version of it, so you can get 6 of these profiles from core to the edge. Good. And you can see here that it's able to reproduce offline analysis, and it doesn't have this weird current profile here is the edge weirdness. We don't have that kind of stuff, which is good. And you can say, okay, this is good. Surrogate models, you can do this, but what is the other use of this? Well, one thing that's problematic, like I said, is that when you're in neutronic environments, you're going to have a lot of issues. So sometimes diagnostics might fail, you might have noise, other issues. So the first time we ran this algorithm, our Thompson scattering basically failed. These lines are not, these are straight, meaning that not that the Thompson measurements is straight electron temperatures, but that they just failed. Someone just yanked the door and the cables got stuck, I think. But in that position, we still can find the density and the temperature very well. So what's happening is when we were training this neural net, we're putting a lot of bad data. We were putting in garbage information, like what if some of the training information had none of the diagnostics, some of the diagnostics fail. We put a lot of noise. So you can basically put a lot of bad issues that you might encounter in a reactor in there and train it with that. So your neural net now learns to ignore bad data and interpolate other information to find your profiles. So this is great. And in the second shot, lo and behold, another discharge, another diagnostics, charge exchange, we failed, but we were still able to get the ion information, even though we didn't have that. So this is great. So what this allows is if you were to try to make a physics-based model where you try to write, if this diagnostic fail, do this. If that diagnostic, do that. If the diagnosis goes above this, do that. It becomes infinitely many if and then statements, and it becomes very hard. But with neural nets, you can do this quite fast without having to worry about writing your if and then statements, which becomes quite large. So this is great. So we can make surrogate models, but the question becomes, why do we use this physics-based models to start with? Why can't we then, instead of going from diagnostics to physics-based models to physics parameters, can we instead go from diagnostics directly to other diagnostics and predict the future of these diagnostics? So using machine learning. So skip basically all the physics. So we tried to do that. We call it diagnostic-to-diagnostics, diag-to-diag. So we take one diagnostics, in this case, electron cyclotron emission, ECE, which are shown here in green. And we try to predict these line measurements, these 4 line measurements that are shown in yellow here. One is electron density, the other one's temperature, so they're not very correlated. They're correlated, but they're not the same thing. So what this is able to do is measured diagnostics are here, and reconstructed are here. So you can see that you can get a very good reconstruction of this interferometer data And you can see that the prediction based on both these models, both the reconstruction and the real measurements, give you exactly the same prediction of some score that we have. So this is great. So you can say then, okay, I can make a big matrix of mapping each diagnostic to another one and see which one has more information about the other one. And I can do this for different channels as well, and then figure out which minimum set that I need for a reactor. So this is great. So you can go a bit further than that and say, okay, so you can do discovery of unseen physics with multimodal super resolution using machine learning. So in this case, what we're looking at is we have some diagnostics that are very high frequency. They might be megahertz that are shown here. So for example, one of them is interferometer, the other one is magnetics. But then we have this very localized good measurements of temperature, for example, using Thomson. But this is maybe 20 hertz instead of megahertz. So you see here the data, but we want to see this event in this diagnostics, this tiny thing, but because our resolution is low, we can't see it. So the question becomes, can we combine the information from the high resolution diagnostics, this low resolution diagnostics into one, and get super resolution, multimodal super resolution to find this event? So we did this, and we can see here for the density measurements and the temperature measurements at the edge. So these are the measured, the black line ones, and the blue is the super resolution version. And you can see that we're able to get very good here, the density measured versus predicted. And we're able to get pretty much what's happening, even for events that are very high frequency. So here, this ELM event is happening really fast. And here's the same profile. This is the measured profile, another measured profile. And we can fill in the blank and see this crashing of the edge of the plasma and building up. And this allows us to then say, okay, well, there's all this interesting physics here. Can we see that? So we looked at that, and this paper is in submission now, to see this tiny island. We have this tiny island when we have edge localized modes suppression. These are so small, they're like in millimeters range. And you see there's two islands here and one island there. And this leads to the flattening of the profiles there. And these are not, you're unable to see this with normal diagnostics, but you can simulate it as shown here. And we did this diag-to-diag megahertz reconstruction, and we can produce exactly the same thing as what was predicted from the simulation. So we can see the flattening here and flattening there, and pressures building up. So this allows us to, this has been a predicted but not being able to find physics that we were able to achieve and see with machine learning. So, okay, so we can see things and we can find our state. Then we want to see the future, right? We want to be the fortune tellers. That's what you want, to be able to control the future. So that's the evolution prediction. So for that, what we do is we take the historic data of the plasma and the actuators, and then we put in the future of the controls, and then predict what the future state of the plasma is going to be. And we develop a neural net just from the data. This is from only historic data that can predict what the future profile is going to be. So here, for example, this is the rotation initially, and we're able to see what's happening in the future. So we are here in time t, and time t plus 200 milliseconds is supposed to go up here. It's the reality versus the prediction. So we can see this for different diagnostics. So at the end of it, you get a dynamics model from only data. So you're just basically putting all the historic data and training a neural net from it. And you can see if I put beam power here, how my beta n goes up and the rotation profile changes and temperature changes. So you can run a whole discharge of a plasma, fusion reactor plasma using this. So yeah, you start from nothing, you increase the rotation and density, you can see that. So this is not an exciting shot, but for a more exciting shot where we increase and reduce the power in there, you can see the density building up, temperature building up, And when you reduce the power, it goes down and it goes up again. So this is great. So you can predict the future based on this, and using a neural net, then you can use this. But another way is to do simulation. So you can use simulation to predict the future of the plasma. We have these very complicated physics modules that can do plasma turbulence analysis and so forth. What we wanted to do was to bring in DIII-D at the US and ASDEX in Germany, the data from both these machines and simulation from transport codes, they're shown here, and combine them to see if we can make simulations of the first to see if we can how good the simulations are, and then adding the simulations and experimental data, see how good we can do. Well, first, what we did is to look at the most known and famous transport codes, ASTER and TRASP, to see if these transport calculations are predicting and how good they are. So what we see is that if you do a p-test is the hypothesis that these transport codes are significantly better than baseline. Baselining is just a scaling law, basically here. And what you see is that for most of the stuff, the hypothesis is not passed. So you don't pass this hypothesis for temperature predictions, for example. You do pass it for power predictions. So the point of this is that the simulations are very hard. As you might imagine, fusion plasmas are hard to predict with simulations. But there is information there, right? This is not that there's no information there. What you can do is combine the simulation and the data and fuse all the information you have from all sources. So for that, we have looked at trying to predict the unseen plasma state. So IP is the current. So these are low performance discharges, if you will, and these are the high performance discharges. So we have a model of the low performance discharges, and we want to extrapolate that to unseen plasmas. So we build a meta learner for that, and then we apply that to predicting other unseen plasmas for extrapolation. So we're building it basically we're building it for known plasmas, and then we use that model to predict unknown plasmas. And then we look at the effect of different sources of information from data, information from, this is a codes, TGLF, and other different types of physics models. And what you can see is that the predictions, the end result is that the experimental data gives the most information. This alpha is basically the logistic regression. So how much of the information comes from experimental data. So we combine two experiments, two reactors, DIII-D and ASDEX. And as you can see, the physics models are not that good. This is the closer towards the right is better. So these are the physics models. These are the machine learning based the experimental data models. And these are different types of combining transfer learning and other. And as you see, when you combine them both, experiment and simulations, you're able to get much better results. And one thing interesting is that if you try to do very complex learning, as opposed to simpler analysis, your prediction goes down because there's a lot of noise. So you might end up overfitting. So just simpler learning methods do better. But the point is that most of the information is coming from data, but simulation is helping, but only marginally. So once you have these predictions, and you can use this to predict events, not only the evolution. So here we're looking at some events called alpha and eigenmodes. So here's the ECE, electron cyclotron channels. There's 42 of them here. And this is what the ECE channels look like. And you enhance the spectrogram. And from that, you can find different types of, you can classify the types of alpha and eigenmodes here, TEs, RSAs, etc. And then you can find where they are. It's close to the edge or is it close to the core? So I'll show you how that works. So this is the spectrogram of one channel. This is the enhanced spectrogram. So right now there's nothing, but you start seeing these events here. And these events, you can see here, we classify them is RSAE and TAEs. And now you see they're going from rho equals 1 towards rho equals 0. So they're moving inwards. And the modes are now gone. They're just gone now. Okay, so this is something that can be done. So now we know where we are. So we know our state. We know what type of modes there are, everything we need to know. So the eye is working fine. So now we need the controller to decide what to do. What is the hammer going to do? So for that, we looked at different applications. One of them is this edge instability. So as you see here, there's this perturbations that are kind of coming down, and these perturbations hit the wall in the bottom. So these are the edge bursts. So bursts of plasma comes out and hit the wall. But if you apply 3D fields, these 3D external fields, you can basically stop this from happening. You see here on the right, it's kind of stabilized. These edge bursts are not going down. And you can do this to suppress them. An interesting thing is that if you try to do this 3D perturbations, here I'm increasing 3D perturbations. These are the instabilities. Each of these lines shows an instability forming. At some point, you get rid of the instabilities. This is the suppression. And when you increase the 3D perturbations, you get rid of it. And then when you reduce it, you start getting these instabilities again. But the annoying thing is that our confinement, the beta here, is going down when we do the suppression, and it goes up again as we get out of suppression. So, but there is a hysteresis. So the way you get in and get out is different. So this allows us to do some dynamic games. So you can go in and play around in there and optimize for the best option. And we did this in one of the machines at K-star. So the confinement is going down here as we increase the 3D currents, as you see. And then we can then reduce the RMP, the 3D perturbations, and the confinement goes up, or you get the instabilities again, and then you can go on doing this. And in the end, you get to a higher confinement and no instability regime all the way here. There's more to be shown here, but at the end of it, we have to do this, we have a neural net of some physics model of how this 3D perturbation works. That's the GPAC and equilibrium that I talked about in cake. And we can then control all the upper, lower, and middle 3D perturbations to get to a state where we don't have instabilities and we have quite high confinement. And this allowed us, the end result is shown in this plot. This is the G, the fusion gain versus the H98, like confinement. And all the modes, all the discharges that didn't have any instabilities is shown here on D3D, the yellow one. And our discharges were able to achieve substantially higher, the highest confinement shots, most confinement shots without any of these instabilities in D3D and on K-star. On both machines, we had the highest efficiency of confinement. And this allowed us to get the longest charges in this K-star. And this was published by Sun-Kyun and Nature.com. So another way to look at this is to say, well, I don't want to look at the measurements and then design my controller independently. I can say, what if I do this whole thing together? I take my diagnostics and feed it back into controllers directly. So combine these things. So one way to do this is reinforcement learning. You probably heard of this. Here's an example from DeepMind AlphaStar, where it's basically just, you just say, here's the game, go play the game, and you have some sort of a loss function or close function where you say, the aim is to gain points, for example, and the more points you gain, the better it is. So it uses this information that gaining points is good and plays the game by itself. And at some point, it becomes so good at it that it wins against all the humans. But in our case, like I said, we don't have a good simulator like this video game, but we do have a database models that we talked about. So we can have a database reinforcement learning. So again, in reinforcement learning, we're asking the deep neural net to find the best action, the control policy. So we have the agent, the RL agent, and it's going to the environment. This is the database model of the fusion reactor, and it's playing games. Basically, it's using the actuators to poke the plasma, and then find them the best actions. So what is the best actions that leads to the award? And in our case, we say, okay, avoid instabilities, that's one, and enhance the confinement, get to the highest performance. Highest performance without instabilities. So we implemented on D3D. Here's what it kind of works. So you actuate and you get to some stability limit maybe. And if you predict you're going to come there, reinforcement learning say, oh, I should go down. And then it says, oh, well, you know, if I have another instability here, I should go down here. And then there's another stability, I go up there. So by doing that in the blue one, you avoid this disruption and stability. While in the other one, the black one, you kind of run into this destabilization and disruption of the plasma. And by doing that in blue one, for example, you get to the highest confinement. You can increase your performance. So for that, we have all these measurements that we combine to predict our state and the instabilities. And we have the controllers here, the electron cyclotron heating, neutral beams, magnetic coil fields, etc. And the agent is in real time predicting how things are going to evolve in the next 25, 50, 100 milliseconds, and then acts on that to avoid instabilities. So there's a video of this that was made kind of like a show for this. Okay. And this was shown in the, let's see.
And paving the way towards unlimited clean energy for us all.
And this is from the event where you see the tokamak here, and this is the plasma, and
paving the way towards unlimited clean energy
and then
for
we
us
see
all.
instability, this island instability forming, and the controller is adjusting so that it avoids all these unstable regions here, and it kind of stays.
All.
All right. That was some examples of how we use this for control purposes. Another thing you can use machine learning for fusion is large language models for operational co-pilot. So these are the students that worked on this, mainly from Princeton University, CMU, and MIT. And for this one, what we're doing is we have a lot of experimental text that's related to the knowledge and fusion area. So we have logbooks of what happened. We have papers and books that tell us about fusion processes and how these experiments are being conducted. We put all that together and combine that with a large language model that's like GPT, ChatGPT. And then you can come up with a language model that can answer your questions about the fusion reactor. So we made this for D3D fusion reactor. So that's we call that chat D3D. And you can then ask questions about different physics phenomena and get some answers. For example, you can ask, how do you quantifiably determine a tearing mode, for example, tearing mode, and it tells you some of these options here. It says you can use Doppler backscattering, cross-polarization scattering, etc., to find these tearing modes. And you can, for example, ask how to turn on the predictive control in PCS, and it goes through how to choose different clicking through So you can, for example, you have to first choose the algorithm, then you select the category under shot profile predictor, and then you can perform these next steps. So this is kind of useful for a new person starting operation, and this was presented at NERPS. And as a conclusion, I talked about different types of controllers and different types of analyses that AI and ML is helping in Fusion. One of them is reinforcement learning control that achieved instability-free operations at D3D with high performance. Here you see the discharges in the black one. Here we're setting the instability limit, and the plasma just dies, goes to 0. And in the machine learning controlled one, it's able to achieve high performance by, here's the beta, it's able to achieve the high performance without going into instabilities. Another example is the edge instabilities. We talked about the highest confinement fusion gain value is achieved without edge disturbances on D3D and K-star, both these machines. So here you can see the fusion gain versus the H98, the confinement sort of. And we were able to achieve the highest confinement fusion gains without edge disturbance on both machines using this AI/ML controllers. And I did talk about the RT cake. So this is the consistent automatic kinetic effects. So we talked about how we can find the state of the plasma, that is the shape and the profiles, that is the temperatures and the densities, and using machine learning and how AI and ML helps in there. We talked about how if you have noise or problems with diagnostics, they might be failing, how AI ML can allow us to avoid these issues. And finally, which I don't have it here, but I'll go back. And another one is finding new physics, which I explained here, which is when we have information that's hidden that we know we can use, but we don't know the physics model that we can use that for example. So we know that there's information from electron cyclotron information from beam emission spectroscopy. There are megahertz. And we have information that's from Thomson scattering, that's 20 kilohertz. We know that these are somehow related to each other, but we don't have really proper equations. And even if we have them, we can't probably solve them. But we can tell to the machine learning algorithms, well, we know these are somehow related to each other. Can you combine this information and give us the full megahertz solution for all the diagnostics? So we're basically using this now to find megahertz profiles and state for the whole fusion reactor. And we show that we can do this. It works quite well, and to get megahertz information of the profiles. And it allows us to find physics that are very intricate. We're talking about finding millimeters to few millimeters scale islands that you would think you wouldn't be able to see with the diagnostics you have, but by combining all the information with machine learning, you are able to achieve that. Thank you very much, and I'll end my presentation here. I think we have lots of time for questions. Probably went a bit faster than expected, but I'm sure there's a lot of questions about fusion.
Yeah,
I'll
thank
answer
you
all
so
the
much,
questions.
Edmund.
Yeah, other than, when is fusion going to be available on the grid?
Okay, so thank you so much for such a detailed presentation. And indeed, we have some few questions here, and I'll take them one by one so that we have time so we can just go through them. The first question is, could you share more details about the NN architectures you used and the training processes and challenges?
Okay, yeah. So I kind of it depends on the audience, but for this audience, I didn't go into details of the specifics of the neural nets. can try to get some information on that. But mainly what I can say is this. So we try the most known and state-of-the-art neural net structures, and we are agnostic. So whatever works, we kind of stick with that. We start with the simplest, and then we start increasing the complexity until we get to something that we're happy with. It's kind of an iterative process. So you start with like convolution neural networks, CNNs, and then you kind of build up the complexity until you get reasonable predictions. That's usually how we do it, because we're not, if I may say so, I'm not well, I do have collaborators, which I didn't talk too much about, but I lead a big machine learning and AI for fusion collaboration, and I have collaborators in Carnegie Mellon University that are very good in developing different types of algorithms, neural nets, and so forth, and uncertainty quantification systems, algorithms. But generically, we're focusing on application on fusion as opposed to trying to come up with new ways of developing neural nets. So we start from the simplest, let's say CNN, and we build up until we get to the point where we think we got the results that are necessary for our case. I hope that's enough. Or I can, you can look at the papers as well to see the details.
Okay. Thank you so much. So another one is, could you give us an overview of where the problem of plasma control falls and the overall landscape of challenges towards viable fusion tech?
Okay. So if I may go in here, so there's a lot of challenges to fusion. One of the issues is, like I said, the instabilities, and I showed an example of this and how it might damage the walls. Here's an example of plasmating the wall. And here's another example where it hit the wall and caused damage to the wall. So this is one of the challenges. This is not the only challenge. I can give a non-exhaustive list, but one of the issues that I work on and as well is superconducting coils. So we need to build superconducting coils that can stand the mechanical forces and neutrons that are coming from the fusion reactions. So that's one of the challenges. We need to build materials that can handle the walls of the reactor, that can handle all this fusion energy that's coming out. That's another. So we have material problems. Superconducting coils are, again, material problems. And we have some other problems, but I would say, generically speaking, big issues are materials, and people are working on that. And another issue is instabilities, which I'm working on. So this is not the only problem, but this is one of the problems.
Okay. Well, another one is, if you fed the neural network with historical tokamak data, would that be reliable and useful in case of building new machine of similar size and operation parameters?
Okay, so that was I maybe went through a bit fast, but let me try to explain what we did. So here is that example. So we were looking at how would you start operating a new machine. So when you start operating a new machine, you start with very low current plasmas that are just tiny, and you start increasing it. Like, for example, this is a megaamp. You're supposed to run at 10, 15 megaamps. So you start at, let's say, 1 megaamp, you go to 2, 3, 4, and up. So the question we were trying to resolve in this was to see if you can extrapolate from 1 to 2 or 2 to 3, because that's how you're going to be operating the machine. And when you're doing this extrapolation, as everyone kind of is aware, machine learning is not that good with extrapolation. So we wanted to see if you can combine physics models with multiple machines. Here we're using the machines, we're using DIII-D and ASDEX to try to predict another machine. And it turns out if you do that combination, you're able to achieve reasonably well predictions of how plasma is going to evolve, even when you're extrapolating. So it's my intuition that this type of extrapolation is reasonable to be able to design the controls that we need for ITER reactor and future fusion reactors. Is that roughly the answer? I suppose.
I hope so.
I
And
hope. Yeah.
another question is, did you use physics-inspired NN architecture? And
Oh,
how do you
yeah.
guarantee that the RL control doesn't move to control regions which are far from the data manifold you trained on?
Okay. So about the pins, the physics informed, we did not, but my well, let me go back to that. Let's see. So yeah, so for this one, the person who was working on this was Jimin, and he's now a professor in Korea, and he's working on applying physics informed neural nets, pins. I didn't. We tried. I mean, we tried, but generically, that was that wasn't that successful, in the personal opinion here. But the reason for that is, I think, comes down to what I showed before, which is that the predictions of physics wasn't that great. So the experimental data was much more reliable in building the machine learning algorithms and predicting. So when you have physics-informed neural nets, that usually works if you have good physics models and you're adding a bit of like data on top, if you will. But ours is kind of the other way around, where we have data-based models where we've been adding a bit of physics on top. So that we tried, but I don't think that was as successful. But Jamin is trying it in Korea to go on that. The pins. And what was the second part again?
The second part is, how do you guarantee that the RL control doesn't move to control regions which are far from the data manifold you trained on?
Okay. Yeah. So, well, in our case now, we know that to be true, but in a reactor, what you need to do is basically a two-stage control. So what we kind of think about is you have a region of control that you know your algorithm is capable of controlling. In an airplane, for example, when you're controlling the airplane, you go and test the airplane up to, for example, angle of attack of 10 degrees. And the controller is able to work in those regimes, then it's all checked out. If the control attack goes above that, well, the control is not designed to do that, so you have to do something else. In fusion reactors, so we have something like that where we say, okay, here's the regime where we feel comfortable controlling. And if it gets out of that, what we do is we turn down the plasma. Basically, we shut down the reaction so that we go into a control shutdown or into a stable regime. So basically what you would have to do is set the parameters so that if you move outside of that manifold or whatever you want to call it, you basically do not use the control there. In our case, we didn't have that problem. But generically, if you have that, you need to put the bounds in. Yeah.
Okay. So, further comments on this question. He stated that it's a bit surprising that the purely data-driven extrapolation generalizes so well in combination with control.
Well, there's a well, so well. There's always I didn't give exact numbers here. I can show you the exact numbers. But let me try to go to that slide. Where is that slide? So so these are some of the predictions for the meta-learning and extrapolation data. So the point here is that the extrapolation that you learn with data plus the simulations, but mainly data, right, is not perfect at all. So there's a lot of error bars there. So if you look at the error bars here, okay, there's a lot of, oh, okay. The error bars are substantial. So I wouldn't say they're amazing, but when you're designing a controller, the question isn't about finding a perfect physics model. It's about finding a physics model that's reasonable enough. So for these cases, well, I can show you some. I don't know if I have some of these error bar plots here. Let me see. Well, this is kind of an error bar plot, but but you can see that the error bars are not that small. These are reasonably large error bars. But those are good enough to be able to do the control, if one may say so. So extrapolation with data is not easy, but we're not extrapolating extremely far. We're extrapolating only minor outside of the region and then doing it bit by bit. And the second part is that the model isn't that amazing, but to do control, you need only a reasonable level of I'm getting some phone calls here. One second. Yeah, the control only needs to be so good. It doesn't need to be perfect. Yeah, let me turn this off. Okay.
Okay. So another question is can I ask another question or want to continue?
Yeah, I'm listening.
Okay. So when generating super resolution diagnostic output, how do you know the NN is not hallucinating the filled-in data?
When you're okay, when we're doing so which one is this? Okay. When generating super resolution, how do you know? Okay, it's not hallucinating. Okay, that's a perfect question. So we do extensive testing. So for that, I'll have to share my paper. So let me try to share let's see if I can find the whole paper here and share it. So we do extensive testing of that. Otherwise, you are right. This would not work out. So let me share my screen and go to that. I hope you see my screen and the paper. You see the paper, Ursa?
No, I still see the PPT.
Okay. All right. How about now? You see the paper?
Yes.
Okay.
Yes, now it's
so
visible.
We test the calculation. So there are some shots where you can get a bit higher resolution. Thomson, for example. And if I may go down here. So we did extensive analysis of the uncertainty quantification for these discharges. And we did analysis of there are some burst modes of Thomson. So we can look at some data sets where there is more data than you would expect for these diagnostics and see if we can match them. And basically, that's how you end up doing this. You basically do extensive uncertainty quantification and looking at cases that are interesting in the sense that you have more data than you would have expect, for example, in Thomson, and you try to you try to use that information to come up with reasonable expectation bounds. But then the question really ends up being, can you ever trust anything perfectly? Then the answer is, to be honest, you have to check your results, and with any diagnostic that is nonlinear, even if it's not a neural net, any that's not nonlinear, you have to figure out how you're going to double check that information. So that's generally how you can do it. But again, because you're doing this nonlinear transformation by filling in the information, you can never get 100%. But what you can do is get reasonable bounds and use that as a guiding post.
Okay. So thank you. This is our final question. Generally, do you have a way of knowing or quantifying a threshold of when your models begin to break down?
No one kind of. That's a good question. Begin to threshold. We do try to do. Well, I guess, yeah. I mean, what we do usually is, let me try to show my figure if you see it. Do you see my screen again?
Yeah.
Okay.
Yes.
If you see what we do here in this one and many other ones is you run multiple different models and you do ensemble, and you come up with some sort of like an error bar, right? You have some sort of an error bar for your prediction. And what we try to do is when your error bar is, let's say, 2 sigmas or some sigma 1.5 outside of your region, then you can say at this point, I really am not able to predict anymore, and I'm not able to do good predictions and do good control. That's how we generally approach this, if you will. So if you were to do uncertain quantification, some sort of UQ or some sort of ensembles to come up with these error bars, what you then ends up doing is you have some bound that you trust, let's say 1 sigma or 2 sigmas. Then you say, whenever I get out of this range, then I know that my models are totally incorrect. So I should just stop using these models. That becomes some sort of what I said previously, where you say, okay, there's a region that I think my control is going to work. And when I'm outside of that, it's not, I don't believe that it might not work. So then I stop using that control it, and then say, okay, my plasma is in a weird state. I should just ramp it down and turn off the fusion reaction.
Okay. So thank you so much for such an enlightening presentation and the questions. Yeah. And if maybe need further. Yeah, that's the last question because we have low time. So
yeah.
So
I hope it answers some of the fusion and how AI and ML can be useful in fusion, just like it is in some other fields.
Yes. So thank you so much, and we hope to have the recording of this as it's on YouTube also. So if you need any information about this, you can also check that out. So thank you so much, Professor Coleman, for such an interesting session. Okay.
Thank you.
Thank you. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.